Alrighty, so it is 11 o'clock, so we will go ahead and get started with class today. First, a few reminders. So your project and group selection, that is due tonight. So if you have not yet selected a data set and who you want to work with, be thinking about that. This is really as simple as choosing a data set and then filling in a short text box, letting me know who you're planning on working with and what your data set is. Are there any questions about this stage of the project? Yes?
We can all, like, because I heard talking about how they're going to use Zillow, we can, like, all use, like, it doesn't have to be, like, unique.
Absolutely, yes. So they do not need to be unique data sets. If multiple groups have the same data, that's totally fine. Yeah?
Will you tell us if you don't like our data set?
Yes, so I will leave a comment if I don't think your data is suitable. So far, everyone has submitted a suitable data set. Other questions? Okay. So that is due tonight. Other assignments that are coming up. Homework 3 is going to be due a week from today. It'll cover cross-validation, which we will finish today, and elastic net regression, which will start today. Likely will finish on Thursday. Typically, I accept late work up until 3 days past the deadline. However, in the interest of getting solutions out to you guys before your midterm exam on February 20th, I will not be accepting any late work for homework 3. That'll be a blank, no late work policy. Any questions about that? Yes?
For those of us who don't show up on Thursdays, when will we be taking the midterm exam?
That is a good question. So physics people, talk to me about scheduling an alternative exam. That date was chosen because I will be at a conference that date. However, my flight leaves February 19th, so Wednesday at 5 p.m. So anytime up until then, you guys can take the midterms. So let me know what works for you. Other questions? Okay. So let's jump into cross-validation and talk a little bit about some other techniques for cross-validation that are available. So one technique that we can use to perform cross-validation on a model or a data set is something called resampling. So the idea behind resampling is that we get an idea of the variation in our original sample by repeatedly drawing samples from a training data set and then refitting the model of interest. What that does is give us a way to quantify the variability in those original model estimates. So rather than fitting the model on the training data once, we'll take a sample from the training data, fit the model, take a sample, fit the model, and so on. So this tells us about the variability of those model estimates, especially in a situation where we're sensitive to tuning parameters. Like for example, k nearest neighbors. This might give us a sense of how variable that optimal k actually is. It also can give us an idea of the sensitivity to extreme values. So how much impact does an outlier have on our estimates, for example. And then finally, it gives us an idea of the sensitivity of the predictions. So we can make predictions on that training data using each of these estimates to get an idea of how much those predictions are going to change before we go out and let loose on the testing data. So the idea here really is that we're taking training data sets from our training data set to get an idea of how sensitive this whole model process actually is. We've been doing that this whole time. It's actually built into the caret function. We just haven't really talked about what that means. So whenever you look at output from caret, you likely see something that says 25 bootstrapped samples. Sometimes you get different estimates each time you run those caret algorithms. That's because in the background, we're doing this resampling process already. So it's just another layer of security, if you will, that our model estimates aren't just a one-off, that we're sure confident about the fitted model. So let's take a look at an example of how this works. And we'll take a look at an example from the breast cancer data set. So this data set, again, we've seen comes from University of Wisconsin-Madison Hospital. We wanted to classify samples of samples of cells as coming from either benign or malignant tumors. So our variables, we have cell thickness, cell size, cell shape, marginal adhesion, epithelial size, and so on. All of these are scaled from 1 to 10. So 1 being in that lowest 10%, 10 being in that highest 10%, all the way down. So let's get an idea of what this is going to look like by fitting a model. So we might fit, for example, a naive Bayes model. So we will start. First thing I'm going to do, though, is only retain the complete cases from this. So there are missing values in the original data set. I'm going to use this complete cases command up here to only keep the rows that have all observations present. So that gives me a data set with 683 observations. The other thing that I'm going to do, and this is a little trick that we had to use last time, in the ML Bench library, all of these variables are pre-loaded or pre-recorded as factors. For our purposes, we're going to treat them as numerical just so we have a little bit more opportunity or availability of models to work with. So I'm going to go through and reclassify each one of these as numeric using the as.numeric function. I'll create my data partition. So here I'm using a 75% split to my training data, create my train and test, build my naive Bayes model. So we'll look at this naive Bayes model. What we see here is this resampling. So we've been using a technique called bootstrapping throughout. Some of you learned about bootstrapping in an intro stats class or in data science, some didn't. The idea with bootstrapping is that we're building samples by taking random resamples from our original data. So think of it like drawing a sample of cards from a deck, but each time you choose a card, you put it back in, reshuffle the deck. So these observations are allowed to repeat in bootstrap sampling. Bootstrap sampling produces biased estimates, but it's really good at estimating the variability of the underlying data. So that's why we like to use this routine. So bootstrapping is going to help us estimate the underlying variability of things like the tuning parameters. So we'll resample. By default, we'll do 25 replications. Each of these is going to have the same size as the original training data, so there's going to be some repeats in these bootstrap samples. We'll then take those bootstrap samples, combine them together to get an idea of this accuracy. So this accuracy in kappa isn't calculated on a single instance of the training data, but rather a weighted set of bootstrap resamples from the training data. That's why even if you're using the same seed as another student, if you're running this the same time, or if you're running this different times with the same training data, you might still get slightly different accuracy in kappa. This is also why sometimes you'll see error messages pop up no time, maybe a few times, or maybe lots of times. It's all dependent on what those bootstrap samples are actually looking like. So that's our sneaky cross-validation that we've been doing. There are some other more explicit cross-validation techniques that we can use. So far, we've been using a pretty simple one. We've just been splitting our data into testing and training. Other cross-validation techniques that are available to us repeat this process. So the method that we've been doing is commonly referred to as the holdout method. So the idea is that we're holding back a portion of our data to test the model on. We'll train or we'll build the model on some other portion, And then we'll keep this test set out to make our predictions, evaluate how well the model is actually doing. The idea here is that we don't want to cheat when we're selecting the best model. We want to have a set of data that hasn't been used, that isn't included in the model, to see how well we are actually doing, to help us prevent that overfitting to our data. So this test set sort of replicates the experience of having real new data in the wild that we're going to test this model on, or that we're going to apply it to once we've built it. These percentages, we've talked about this a little bit before. Arbitrary is a good word for what they are. There's really no hard and fast rule. Depending on how much data you actually have available, you might want to adjust the size of the split just to make sure you have enough data in each of these groups. There are a lot of pros to this method. We have a lot of control in terms of how we're selecting the size of the testing and training data set. That's completely up to us. Conceptually, this is a pretty simple process. We can implement unbalanced sampling, so we can choose our testing training sets completely at random, or we can try to make the testing and training sets look similar in terms of our output feature, so create a balanced sampling split. No matter which technique we do, this is pretty easy to implement. The cons here, we do have to make a choice. We have to choose the size of the testing versus training data set. Any choice that we make is going to perhaps affect the model accuracy, maybe in a good way, maybe in a bad way, but those choices leave us open to criticism of the model. So we have to be able to defend those choices somehow. Each of these splits, as you've seen, does result in slightly different samples with slightly different performances. Just due to random chance, some training data sets might be better suited or might produce lower error than other training data sets just because of random fluctuations. And then finally, we do lose some information when we do this. We're not using all of the available data. We're purposefully leaving out some information that's available to us, which means that we're sacrificing some of that precision by removing data from our model. So what I wanted to do was get an idea of how sensitive this holdout method actually is to the original training data set. So how much fluctuation are we going to expect to see from training data set to training data set in terms of how our model is fitting? So here what I'm doing is modifying this create data partition command just slightly. Instead of using times equal 1, I'm using times equal n, and I want to show you what that creates, or what we get when we do that. So I will switch over to R. I'll zoom in a little bit and look for this section in the cross-validation notes. We'll run everything before just to make sure all my packages are loaded. So what is included in this train index sub I data frame? This is actually going to be a matrix, so not a list of rows. What's included is a set of resamples. So we have our first sample. These are all of the IDs that will be assigned to our training data set, or all of the rows. The next column is a separate sample, and then another sample, and then another sample. So each of these columns represents a different way to allocate observations to the training data set. So then what I'm going to do is for each of those subsamples or each of those partitions, here I'm doing 50 of them. I'm going to iterate through each of the columns, and I'm going to keep track of those training indices. So I'll define a new training and new testing inside my loop. I'll fit the model inside the loop, and then I'm going to store out two things. I'm going to store out the accuracy and whether or not we're using a kernel, since this is a naive Bayes approach. The idea here being is that we're going to get an idea of how these two things change, accuracy and whether or not we use the kernel approach, based on different choices of the training data. Are there any questions about what this code is doing? I also recorded how long this took to do. So this represents 50 different runs of fitting the model using a different training data set. Took under 1.5 minutes. So not too long to do. Here is what I got. So on the right, or on the left, excuse me, what you're seeing here are the different accuracies that were obtained. So the accuracy based on the different training sets that were used ranged from about 0.955 to 0.980. So there's some fluctuation in the accuracy, but not much. Whether or not that kernel density estimation was better, most of the time it was. There were, however, a few cases where kernel density estimation didn't work as well. So this tells me that most of the time a model fit on this data is going to recommend using kernel density approach and have an accuracy somewhere between, say, 0.965 and 0.97. Now I only did this 50 times. If you've taken intro stats with me, you know that's probably not enough. We can do it more. 50 times took 1.3 minutes. If I do this, say, 500 times, how long do you think that's going to take? 10 minutes, 13 minutes. Luckily, I wrote this code in a way that I only have to change one thing. So we will go to R, let that run for a while in the background. So here's 50, 500. We'll let that go. I'm going to use a library called beep-r to make a beep. And we'll use beep noise 8, so that'll just let me know when that's done executing. And then we'll look at the plot. So this should run next. All right, so get excited to come back to that test validation or that leave one out, or holdout method validation results. And the next type of validation that I want to talk about is one that's going to take much longer. This is called leave one out cross validation. Another term for this is jackknife cross validation. So there's a really simple idea to this leave one out or jackknife cross validation. Instead of allocating 25% of your data to your testing data, you allocate just one observation. So you fit the model with everything but the one observation. You see how well you do on the observation that was left out, and then you do it again, and again, and again, and again. So you end up repeating this process n times. We fit our algorithm to the n-1 data points in testing. We make a prediction for what's left out, and we repeat until all data points have been left out and tested. It's a really good idea in theory. If you have more than 100 data points, get comfortable, because this is going to take a while. So then what we try to do, because we don't want to assess the accuracy of a model based on just one data point at a time. After we fit the model on each of the n-1 n subsamples of n-1 observations, we come up with something called the estimated cross-validation error. So for jackknife or leave one out cross-validation, what we do is just take the average of the error that's obtained when we predict on each of those one data points. So let's say we're in a classification scenario. How would you measure error in something like this? Simple error for cross-validation for classification might be if the actual value of y is not equal to the predicted, error equals 1. Otherwise, if we're predicting correctly, error equals 0. Just use a binary indicator of whether or not we've gotten this correct. Then our cross-validation error would represent the proportion of times or the percent of times we predicted an error. If we're looking at something like the probability of membership within a class, we could also use the difference between that predicted probability and actual class membership to look at the error. So we've got a lot of choices here to measure this cross-validation error. But those are the two most common in classification plan. So I went ahead and implemented leave one out. This looked a little different. So what I've done here is create this testing and training data set. Because it's leave one out cross-validation, I can just do that by removing one row at a time for my training data set and then retaining one row into my testing data set. So that's why we don't need create data partition here. I'm keeping two things. I'm keeping the predicted value, so whether or not we are predicting class membership, so benign versus malignant tumors. Then I'm keeping the probability of whether or not we have a benign versus malignant tumor. Time difference here, this takes about 12 minutes to execute. So it's not quite that bad to do this leave one out approach. Part of that is because naive Bayes is a really simple model to implement. If we were using a more complex approach, like say k nearest neighbors, this would take a really long time to run. The other reason why this doesn't take very much time is that we're making predictions, but we're making predictions on just one value. So that's not too hard to do. So what I decided to do next, because I've got those predictions, I'm removing observations one at a time. So they're in order of the original data. I went ahead and constructed a confusion matrix. So here's how well we did with leave one out cross-validation. Our accuracy is 0.96. We're doing pretty good classifying benign as benign, malignant as malignant, but we do still have some errors. How does this accuracy compare to the accuracy that we got, 0.96, using different iterations of the training data? We're actually on the low end of what we had gotten with the testing versus training data. So it sounds like, in theory, leave one out cross-validation is a good idea. Oftentimes, the prediction isn't measurably better than it would be using, say, the holdout method. Questions? Now there is an easier way to do this. The easier way is to use a function in Caret called train control. So what this train control function does is let you specify how you want to do cross-validation within that train function. So in order to do leave one out cross-validation, your method is loocv, L-O-O-C-V. There are other types of options that are available, including something called k-fold cross-validation. You could implement that using repeated CV, for example. Options that are available, we've got bootstrap cross-validation, we've got leave one out cross-validation, we have LGO-CV, so that's leave a group out. We have repeated cross-validation, time slice, none. Something called OOB, this stands for out of bag, so this is something that applies to decision trees and random forest based models, so we'll come back to that later. If you want to include no cross-validation, you can certainly set that to none. Is this any faster than my simple for loop was? No, it's actually a little slower. In order to implement this in your train function, what you need to do is define an object called fit control, or GR control is what I ended up using. That's just specifying which method you want to use. And then you just add that as an option in train. So this is using leave one out cross validation automated versus my for loop. Yeah.
We can use whichever one we want. This is like a minute and a half more.
Absolutely. Yeah, you can use whatever one you want. Certainly leave one out cross validation is easy to program by hand. Some of these are a lot harder to program by hand. Definitely feel free to go straight to a control option. Other questions? Okay. We'll check on our R process, make sure it's still going. Something stopped. Oh, I have mute on. Sorry, that's why you didn't get to hear the beep. I know.
You're so excited.
I'm dumb. Yes.
Just play the beep, but like set the beep time to like point.
Actually, the beep time might not be going because of the volume. There's the beep. That was delayed.
Such great beeps.
They are wonderful. It's one of my favorite packages. So this is the distribution of accuracy. Oh, snap. Accuracy with 500 looks a lot more like a normal distribution, which I'm not surprised by because everything looks like a normal distribution when you do resampling. So we'll expect to get accuracy somewhere between 0.95 and 0.99. Most of the time, that kernel density method is going to perform better. So if I were trying to make a final decision on whether or not to use this model, I might go with kernel density true.
Could you review what the kernel density method means?
So kernel density method is just a way to model the underlying distribution of those input variables that naive Bayes is using. We haven't really talked much about what it means yet, but we will. Other questions? For now, it's just a tuning parameter in naive Bayes. So one kind of nice in between this holdout method and leave one out cross validation is k-fold cross validation. So essentially we repeat this holdout method k times. So we divide the set of observations into k groups, which we refer to as folds, and then we remove one fold at a time for testing. So we end up fitting the model and evaluating it k times. We're not as slow as leave one out cross validation. Leave one out cross validation is in fact n-fold cross validation. This is a little bit more consistent than the holdout method is because we have that built-in idea of the variability from sample to sample. It's essentially the same process that I was doing by hand with one little tweak. The folds are independent. So in other words, those folds represent non-overlapping partitions of the data that we're keeping out. So one visual way to think about this, we split our data up into 4 folds. So here is our full data set. We've got fold 1, fold 2, fold 3, fold 4. Each time we fit this model, we'll keep one fold or one subset out to do our model testing. In practice, somewhere between 5 and 10 tends to work pretty well. So we don't need to do this a lot. We can use k-fold cross-validation using this train control. So we'll set the method equals CV, number equals 10. That tells me how many folds we want to include. So how many subsets we want to split the data up into. We'll fit this using that k-fold method. Takes about 13.8 seconds. So not much additional time by splitting into those k-folds. So there's a pretty obvious computational advantage here. Instead of splitting our data up into lots of different testing and training data sets, or removing one observation at a time, like in leave one out cross-validation, we're only repeating this process, say, 5 to 10 times. So that is a major bonus. There's also a nice theoretical advantage here. The theoretical advantage is that this k-fold cross-validation actually gives us much more accurate estimates of the test, instead of test terror, this should be test error. Hopefully these models are not striking you with terror quite yet. If they are, that's okay. But we're getting better estimates of the error using this method, or we should theoretically, than we get with leave one out cross-validation. What I'd like you to do is take a few minutes to talk through it with someone sitting next to you. Why would this give better estimates of the error? So our cross-validation error, we defined pretty simply to just be the sum of the errors over all of the n data points, and then we just average, so divide by n. So this cross-validation error you can think of this like the average of the errors. So essentially, this is a sample mean. We're just taking the sample mean of all of the errors. Think back to Introstat. Stat 101, Math 360, 361, Business 229, etc. What is, you should have covered this in all of those. Oh, what is the standard deviation, or sorry, let's do this a little differently. What is the sampling distribution of a mean? Anyone remember? One more time.
Binomial.
It's not binomial. It's another well-known distribution that's used very often We usually use it. We normally use it.
Yeah. Yeah, I thought it was normal, and then median's the funny one that brings out too much.
So the sampling distribution of the mean is in fact normal. The mean is mu, so the population of the underlying variable. So here, this mu is population or theoretical cross-validation error. How do I get the standard error of this distribution?
Standard error on the mean is standard deviation over the square root of n.
Yep.
Standard deviation, central limit theorem.
Exactly. So according to the central limit theorem, that has standard deviation sigma over the square root of n. So here sigma is the standard deviation of the true cross-validation error. And it's sample size. Questions so far? Okay. Now think about what happens under leave one out cross-validation. So each of these errors will calculate. So each one of these subsamples has standard error sigma over the square root of n. And leave one out cross-validation, we're only using one n to make a prediction. We have only got one n in our test, so that's the variation of each of these error terms. So we have bigger variability than we might with k-fold cross-validation. So under k-fold, we'll calculate this cross-validation error over each of the k folds. So then we're doing this error for all of the i's in that k fold. There's n over k observations in each of those k folds. So each of those errors are going to be averages within the k fold. So each of these error terms is going to have less error, which means that that average is going to have less error as well. So the real idea, the concept is that when we're making predictions using this k-fold cross-validation, we can better estimate the error because we're allocating more observations to estimating the error. That error is going to be more consistent from fold to fold than it is going to be from predicting on a single observation to a single observation. So that's why k-fold cross-validation somewhat counterintuitively tends to estimate the error a little bit better. Sampling distributions are important for more than just t-tests. Yay. So there's a a trade-off whenever we're fitting these algorithms. Then there's a trade-off between the bias and the variance. So in statistics, when we think about the bias, it's how far off we are, whether or not there's going to be a systematic error in our estimates. Leave one out cross-validation has the least bias, is least likely to systematically over or underestimate. Hold out cross-validation has the most bias. You're most likely to be off. Somewhere in between is that k-fold technique. There's more variance with that should be leave one out cross-validation. So here where it says more variance, the most comes with leave one out cross-validation. So please fix that in your notes. This is correct. There's less variance with k-fold cross-validation, which we've just used sampling distributions to argue about. So k-fold cross-validation is kind of in between with the bias, has less variance, so we tend to go with that when we're fitting a final model. Yeah?
Where would holdout cross-validation be in variance?
So holdout validation in terms of variance is going to be all the way over here. We don't have much variance because we're only doing the process once. So we don't really know what that variability is going to be. And again, in general, somewhere between 5 and 10 is a good value for K. Any more than that, and you're not really seeing those gains for computational time. Now, the last type of cross-validation I want to talk about is one that we've already touched on briefly. It's that resampling idea, just giving a formal definition of bootstrapping. So bootstrapping is when we randomly select n observations from the original data set with replacement to create a new bootstrap sample. So if bootstrapping is a new idea, which for some of you it may be, some of you it may not, that's the formal definition of bootstrapping. And again, we don't really talk about this too much because it's done by default. All right, so let's say that we want to not implement cross-validation. We certainly can do that. The way we do that is by this. So we'll write train control method equals none. So here's what it looks like when I try to fit the model. I do get an error back. The error is that only one model should be specified in TuneGrid with no resampling. Any ideas what that means? Yeah.
So when you're using TuneGrid, you're just setting certain parameters, but you already set method in train to be naive Bayes, so you can't send it to both naive Bayes and none.
So that's on the right track. So naive Bayes has a tuning parameter. The tuning parameter is this, whether or not we're using kernel density to model the input variables or whether that kernel is false and we're using a normal distribution to model those. If we're saying that we don't want to do any cross-validation to improve the model, well then we have to give it those full tuning parameters as well. So we have to choose which of those two. So here we have to choose whether or not we're going to use that kernel density method. If we wanted to do k nearest neighbors without any cross-validation, our tuning parameter that we would have to choose would be k. We would have to specify a single value for the number of models or the number of neighbors to use. So this is something that we might use when we have, say, a final model selected. We know that k equals 5, for example, is the best, or we know that kernel density is the best. We want to fit a final model on all of our training data. Well, then maybe we would use no. control. Or no resampling, excuse me. So what are the best practices here? So in practice, you'll often see people use some combination of in between. So either holding out some data for testing or using k-fold cross-validation on the training data set. So typically some combination of the holdout method and then cross-validation down underneath. What you'll see me do going forward in the notes is just working with the basic default caret options. On homework assignments, I may ask you to do a specific cross-validation techniques just to get some practice. But for the sake of time for these notes to create, I don't really do much cross-validation in basic examples, just to try to highlight one change at a time. Questions? Okay. And then last but not least, a reminder, if you are doing this, which you will on the next assignment, some of these code chunks are going to take a while to execute. So definitely try to cache if you can. Try to save some results. For example, your homework that is due next week. Is going to ask you to try out some cross-validation techniques on k nearest neighbors with k somewhere between 20 and 50. Part C, if you're doing it correctly, should take about an hour to run.
What?
Correctly or incorrectly? Sorry.
If you're doing it correctly, it should take about an hour to run.
So you can't start this 30 minutes before.
Do not start this 30 minutes before. Make sure you got your code for B and you like it, so just 10 sets, and then go to 50. Maybe it's not an hour. It is.
It's one day. Sorry.
It did not take one day. I might have cut it down at an hour. I promise I do these homework assignments before I assign them. Okay, 1 minute. Okay, I cut it down to about 10 minutes.
Okay, that's fine.
So it should take you about 10 minutes to run that. Yes. That's okay. If you remember,
It was on the top of my head, then I got thinking about how long it takes to run the code.
if you remember, shout it out. There is another hint here. So there's a function in the NNet package. NNet stands for neural net, that tells you which row or which element in an array, for example, corresponds to the maximum. So instead of returning the maximum, it will tell you the row number that contains the maximum. Might be helpful. Yes.
I remember. So
Awesome.
when we cache the what we run, where does that tend to necessarily save to? Will it create its own folder?
Yes. So whenever you cache something, it will create its own file or its own folder. So this is where the cache is stored for my homework 3 solution. So all of that will contain the results of the code chunks. It'll grab those, stick them in appropriately when the document's compiled. So yeah, if you're working in RStudio, you'll start to, as you're doing caching, see a lot of folders. So for example, here are all of my cache folders for all of the notes. These file up quickly. The only time that cache will change is if you make a change to the code. So even if you change just a single character or insert a space in the code chunk, it will re-execute. So again, I recommend that you get code that you like for C and then copy it down for E and just change the number of resamples. Other questions? Okay. The other thing that I should mention throughout this, I did some testing, so I give you some hints for what values you might try in your tuning grid. The actual values that you choose in your tuning grid are up to you, but they should be somewhere in that range that worked. So hopefully that helps you narrow down your grid a little bit better. Okay, so we've got 25 minutes left. What I want to do is start thinking about regression in a machine learning context. So regression here means a little bit more than it does in intro stats. It becomes a much bigger class of techniques. So in machine learning, regression as a technique refers to just making numerical predictions. So instead of classifying to a group, yes or no, we might predict along some numerical feature or some numerical spectrum. In intro stats, regression refers to the simple linear regression model, y equals beta 0 plus beta 1 x, or add multiple x's and extend. Now in other classes as statisticians, we would have focused on inference here. So are those regression coefficients statistically significant? Are they telling us about the relationship between the variables? Here, we're going to be more focused on getting predictions. So what can we do to get accurate predictions from a regression model rather than making inference? The standard linear model is this, and I write it in extended form with p parameters. So say we have p input features, these x's, they could be numerical, they could be categorical, but we'll predict our output y in just a straight linear sense. So we'll have beta 0, some intercept, plus beta 1 times x, plus beta 2 times x2, and so on, all the way to our p input plus some error term epsilon. So in stats, how do we fit this model? We typically use an approach called least squares estimation or least squares regression. We do this so that we can make inferences about the beta. The assumptions that go with least squares regression are very well suited to testing whether or not these regression coefficients are, for example, statistically different from 0, whether they should be included in the model or not. Once we step away from inference about beta being our primary goal, once prediction becomes the goal, we open up a lot more estimation algorithms. So we open, for example, regularization algorithms, lasso regression, ridge regression. So we'll talk about least squares, we'll talk about regularization methods, we'll talk about the elastic net as well. So let's talk about least squares regression and what this does. So notationally, I'm going to let y hat I represent the predicted value of y for some set of inputs. Least squares regression is so named because it estimates the parameters subject to two restrictions, subject to criteria. So we'll set the sum of squares for the error terms to be 0. So we'll choose those beta 0, beta 1, beta p, such that the errors, so yi predicted minus observed, those sum to 0. We're also going to minimize the squared errors, or the sum of the squared errors. So I'll take these, y hat I minus y, square them, sum them up, minimize this term. We do that by taking simple derivatives. So least squares regression has a lot of nice features. You can solve these least squares equations analytically. It's a pretty easy matrix representation of the least square solutions. You can also tweak these ever so slightly, but they require an assumption, and they require an assumption about the error term specifically. You have to assume that they're normal for this to work. There are a lot of cases where we might want to use something different. So if the true relationship between the response and the predictors is approximately linear, so if all of the x's and all of the y's follow a normal linear relationship, then the least squares estimator tends to have low bias. If that's not true, if the relationship between x and y is not linear, well then fitting a linear trend, probably going to be a pretty bad idea. Not something that's going to work well in practice. If the sample size n is much bigger than p, then the least squares estimates tend to have low variance. They tend to be really accurate representations or estimations of the underlying parameters. If that's not true, then we have another problem. So if n is not much larger than p, so if the number of observations is not much larger, there's a lot of variation in the estimates. We might tend to miss with those least squared estimates. We might overfit. We might have bad predictions. Here's the worst problem. If we have fewer observations than we have parameters, which happens a lot in machine learning, there's not a least squares solution. We cannot find a unique solution to those equations. So that's a problem too. One solution is to constrain or shrink those estimated coefficients. So we'll try to take those betas in the regression equation and shrink them down, artificially force them closer to 0. What that does is increase some bias. If I'm artificially forcing them to be close to 0, I won't have an accurate estimation. I'm artificially forcing in that bias. But what that does is reduce the variance. So if I force those regression coefficients closer to 0, I end up with estimates with slightly lower variance. That lower variance can lead to lower error overall. So that can be an improvement. There are other ways or other reasons why we might want to move away from least squares regression. Least squares regression doesn't remove variables from a model. The variables that you put into a least squares model stay there, even if they're non-important or even if they're non-significant. If we're adding those irrelevant variables, it's harder to interpret the model, results in predictions that might be inaccurate or biased because those variables really aren't carrying any meaning. So maybe we can artificially and algorithmically shrink those coefficients down to be at or near 0 for the non-important variables. So that's what we'd like to do, or that's what we would like a model to be able to do. So alternatives here. Subset selection is one. That's more of a 362-step modeling technique. We do a lot of subset selection in there. So essentially we're looking at different numerical criteria to decide which variables stay in a model, which do not. We're going to work on shrinkage, or we're going to talk about shrinkage models, so fitting this model algorithmically to shrink the coefficients relative to 0. Another solution in regression is something called dimension reduction. So we can take those prediction variables, stick them into an m-dimensional subspace, and then try to use those projections to find new predictors. In English, find linear combinations of the predictor variables and only keep the important linear combinations. Questions? Okay. So before we talk about each of these models, we do need to spend a little bit of time talking about how we're going to evaluate these regression models. How are we going to decide whether or not shrinkage, for example, is actually an improvement? There's 3 common criteria that we will use in a regression model. And again, regression here in machine learning only means that we're making numerical predictions. So example criteria that we can use are something called mean square error, sometimes called mean squared prediction error. So some references will stick a p in there. We can also use adjusted R squared, and we can use mean absolute error. So first, mean squared error. So the mean squared error takes the sum of those squared error terms, or the sum of the squared differences between the predicted and the actual value, and averages them. Smaller mean square error is better. We want those predicted values to be close to those observed values. That'll result in a smaller squared deviation, which will result in a smaller average or a smaller mean squared error. There's no absolute scale with mean square errors, so we can't say that a mean square error of 1 with one data set is objectively better than a mean square error of 2 with another data set. Units matter, the original scale matters with mean square error. Often what we end up doing is taking these evaluation criteria, using them to select which model does best on the training data, and then recalculating on the testing data. Another alternative here is root mean square error. So sometimes we'll take the square root of that mean square error instead. If this is mean square error, what do you think changes for mean absolute error? Yep, squared becomes an absolute value for mean absolute error. One of these is going to be more sensitive to extreme differences. So this mean square error penalizes large deviations more heavily than mean absolute error does. So the other metric that we might use is something called adjusted R-squared. So R-squared represents the coefficient of determination in statistics. Essentially, it's the squared correlation between the predicted values and the observed values. Even if the data doesn't follow a linear trend, if our model is predicting well, then there should be a linear relationship between the observed y's, the observed outputs, and the predicted outputs. So that's what this R-squared attempts to measure. The adjusted R-squared penalizes this based on the number of variables in the model. So adjusted R-squared shifts that R-squared value downward. We want to favor, if we can, models that are simpler, have fewer variables in them. So R-squared is just simply the squared correlation between the true value and the predicted value for the output feature. R-squared adjusted takes this and downweights it slightly. Both of these should be on a scale from 0 to 1. R-squared and adjusted R-squared are absolute measures, so you can compare those from different data sets. Questions? Okay. So let's introduce an example and talk a little bit about ridge regression, and that's where we'll stop. So the data set that we're going to use is called the Air Quality UCI data set. So this is the air quality data set from the UC Irvine Machine Learning archive. You can find the data set at that link. This data set contains 9,358 instances of hourly average responses from 5 metal oxide chemical sensors. So this device was located on the field in a significantly polluted area at road level within a large Italian city. So we placed this device essentially at ground level, and we measured different readings from this. I don't know if the original data says which city this was in. I saw Lorenzo's eyes light up, which is why I wanted to look and see if we can find out which city this is. So here's the article that references this data. A main street located in the center of an Italian city characterized by heavy car traffic.
Could be Milan.
Control F Milan.
Well,
They're they're all in
They're-
Milan.
They're all in Milan.
That seems pretty likely.
Yeah.
The guy at the bottom
Milan
is-
seems like a good guess. So we'll read the data in. I've got this data as a CSV file. I just downloaded it directly from the UCI archive. Here's the variables that we have in this data set. We have date and time. We have hourly CO concentration. We have hourly sensor response for tin oxide, non-metallic hydrocarbons, benzene, titania, NOx, and so on. So we have a lot of different sensor responses. We also have some environmental variables, temperature, humidity, absolute humidity. Those can all affect air pollution as well. So I'm going to use the summary function to just take a look at this data. What sticks out?
Different scales.
Got different scales,
A lot of NA values and some of them.
a lot of NAs,
And MHC has like 1,500.
a lot of NAs here. What do these NAs represent?
Values.
Okay, so we've got empty values. Why would a sensor return an empty value?
Maybe there's none detected.
Okay, so there could be none detected. There could be 0. There could be none at the detectable level.
It could be broken.
Could be broken.
I think they have 0.
So maybe these NAs contain some useful information. Maybe we shouldn't discard them automatically. We do for now, so I will discard those NAs.
We should.
Yeah.
We will talk about a better solution to doing that. Notice though what this does to the size of my data. I start with 9,358 instances. Once I remove every row with an NA somewhere,
Not great.
so we probably don't want to do that in practice. So we'll talk about some better solutions. So for now, we're working with a data set with 827 observations instead of 9,000. Why? So let me show you this full code. Why am I looking at columns 1 through 15 when I do this?
Those are the only variables you're interested in.
They're-
Everything off of.
They're the only variables that I'm interested in. And in fact, something happens when I read in this data exactly how the UCI archive has it represented. So I'll read this in. It has 17 variables. It's actually got more observations than UCI tells me it does as well. It reads it in with 2 extra variables here. Are handles labeling these extra variables with X's, X.1, .2, .3 when things are repeated? How do you think those extra variables ended up there?
I don't know about this case particularly, but I know that CSV files can do that because they don't actually measure size by like what areas are filled, so much as like what's been affected or used.
So their CSV, or this came from a CSV file, so how they store the data can sometimes be related to that. What generally causes this is if you, well, what can cause this? There's lots of causes. But if you take, for example, a text file, convert it to a CSV file, if there are any extra spaces after these numbers for absolute humidity, those are going to get registered as another column. If we scroll all the way down, we get NAs pretty much across the board. So x1 and x2, or sorry, x and x1, those extra columns are both NA all the way through. So we can just cut them out. And that was why I used 1 through 15 for my columns. No matter where you're getting the data from, sometimes things are going to be a little tricky. Looking at this full summary, I see another way that I could potentially deal with the NA problem. Some variables look like they might be more prone to NAs than others. Something else kind of interesting is happening in this data. There are a lot of variables with the same number of NAs. There are a lot of variables with 480 NAs. Now, I'm not a gambling person. Most statisticians are not, but I would wager that that's probably not 480 different observations across those variables. Those are likely time points with NAs across the board, so maybe the sensor broke. So we can dig into those a little more. All right, so we are about out of time. The last thing that I want to show you, because you will need to do it on your homework, is how to implement the basic linear regression model in Carrot. Ordinary or simple least squares regression, use method equals GLM to do this. GLM stands for the generalized linear model. That's a more broad class that allows for Y to be non-normally distributed. But if you use method equals GLM with no other options, this will just fit a basic linear model. Yeah?
So because we're concerned more with predictions and machine learning using regressions, does that mean the data is more likely almost always going to be time series data?
No, not necessarily. So time series data is something that can be used with this. We can also classify with time series data. The main feature that makes this a regression problem is that our output's numerical. So we are about out of time. We will stop here. If you would like stickers, please grab some on your way out, stick them on things, and advertise that we have this cool new program. And I will see you guys on Thursday.